More data is not always better in distillation. In fact, it can actively waste compute. Here's why. Your student model learns the most from examples where the teacher's output distribution is genuinely informative, meaning uncertain, nuanced, or multimodal. Examples where the teacher is 99.9% confident on a single token. Those barely move the gradients. You're spending compute for nearly zero learning signal. This is the idea behind data pruning for distillation. Before you even start student training, score your dataset by the teacher's output entropy or uncertainty. High entropy examples, where the teacher is less certain, are your most valuable training signal. Low entropy, near deterministic examples can be subsampled heavily. In practice, teams have reported cutting dataset size by 30 to 50% using this approach with minimal degradation in student quality, because the student still sees the hard cases. Run a fast single-pass entropy scoring sweep over your data before committing to the full training run. It's cheap insurance. A related technique, curriculum distillation. Start training on the easiest, most confident teacher examples and progressively introduce the hard ones. This can improve convergence speed, letting you reach a target loss with fewer total gradient steps. Even with a perfect dataset, you can bleed money from infrastructure inefficiency. 3 things to audit immediately. First, gradient checkpointing. If you're training a large student, say 3 billion to 7 billion parameters, you're probably running into memory pressure that forces smaller batch sizes, which means more steps, which means more time. Gradient checkpointing trades a roughly 30% increase in compute for a dramatic reduction in memory, letting you run larger batches. Net cost is usually lower because fewer larger batches reduce overhead. Second, mixed precision training. If you're not running B float 16 or float 16 on your student training already, you're leaving massive efficiency gains on the table. Modern H100s and A100s run tensor cores at 2 to 3 times throughput in FP16 versus FP32. There's almost no reason to train distillation targets in full precision. Third, and this one is underrated, I/O pipelining. On multi-GPU setups, your GPUs are often sitting idle waiting on data loading. Profile your training loop and check GPU utilization. If it's below 85%, your bottleneck might be your data loader, not your compute. Prefetching increasing worker count and using memory-mapped formats like Arrow or raw binary tensors instead of JSON or CSV can close that gap significantly.